In this video, I'm going to talk about BERT, which is short for Bidirectional Encoder Representation from Transformers. And this is one of the natural language processing approaches that has got a lot of attention. In 2018, researchers at Google AI Language open sourced the new techniques for natural language processing, which is the BERT, and that was a major breakthrough. It took deep learning community kind of by storm because it was really cool and great, and the performance was perfect. And it is, to be honest, much easier than many other existing approaches there. So if there is one NLP that you want to give it a try, probably BERT is the one. But why was BERT needed, really? One of the biggest challenges in NLP is the lack of enough training data. Overall, there is enormous amount of text data available, but if we want to create task-specific data set, we need to split the files into very many diverse fields, and when we do this, we end up with only a few thousands or few hundred thousands human labeled training examples, and it's not enough. To perform well, we require much larger amount of data, and the huge improvements happens when we train millions or billions of annotated training examples. To help bridge this gap in data, researchers have developed various techniques for training general purpose language representation models using piles of unannotated text from web, and that is called pre-training. And the general purpose of pre-training models could be later fine-tuned for a smaller task specifics. For example, when working with problems like question answering and sentiment analysis, this is a useful approach. And this approach results in great accuracy improvement compared to training on smaller task-specific datasets from scratch. And BERT is a recent addition to these techniques of NLP pre-training, and it has performed quite well so far. So what is the core idea behind the BERT? Think about language modeling. What is it really about? What is the problem that language modeling tries to solve? Basically, their task is to fill in the blank based on the context. For example, the woman went to the store and bought a blank of shoes. A language model might complete this sentence by saying the word cart would fill the blank 20% and word pair 80% of the time. Before BERT, a language model would have looked at this text sequence during training from either left or right, or combined left to right and right to left. And this one directional approach works well for generating sequences. We could predict the next word append to the second and then predict the next to next word until we have a complete sentence. But in the BERT era, a language model which is bidirectionally trained could do much better. This means that we can now have a deeper sense of language context and flow compared to a single direction language model. Instead of predicting the next word in the sentence, BERT makes use of a novel technique called mask LM. What it does is that it basically randomly masks words in the sentence and then tries to predict them. Masking means that the model looks in both directions and it uses the full context of the sentence, both left and right surrounding, in order to predict the masked word. And unlike the previous language model, it takes both the previous and the next tokens into account at the same time. And the other models available, like left to right or right to left LSTMs, would basically miss the same time part. But why is it so important and so powerful? A pre-trained language representation can either be context-free or context-based. Context-based representation then can be unidirectional or bidirectional. context-free models like word2vec generate a single word embedding representation for each word in the vocabulary. For example, the word bank would have the same context-free representation in bank account and bank on the river. On the other hand, context-based models generate a representation of each word that is based on the other words in the sentence. For example, in the sentence, I access the bank account, a unidirectional contextual model would represent bank based on the access, but not the account. However, when we are using BERT, basically bank use both its previous and next context, which is I access the and account. And then as you see, it's much more easier. Moreover, BERT is based on the transformer model architecture instead of simple LSTM. And a transformer works by performing a small constant number of steps. In each step, it applies an attention mechanism to understand relations between all words in the sentence, regardless of their respective positions. For example, given the sentence, I arrived at the bank after crossing the river, to determine the word bank refers to the shore of a river and not a financial institute, a transformer can learn to immediately pay attention to the word river and make this decision in just one step. Now that we know, the key idea of BERT is basically this bidirectionality, looking at left and right at the same time. Let's see how does it work in practice. So BERT relies on a transformer, what I just mentioned, that the attention mechanism that learns contextual relationship between words in the text. A basic transformer consists of an encoder to read the text input and a decoder to produce the prediction for the task. Since BERT's goal is to generate a language representation model, it needs the encoder part. The input to the encoder for BERT is a sequence of tokens which are first converted into vectors and then processed in the neural network. But before processing can start, BERT needs the input to be changed with, modified with some extra metadata. And what are they? There are three of them: token embedding, segment embedding, and positional embedding. Uh, you can have a look at the picture here as well. For token embedding, when we add a CLS token to the input word, tokens at the beginning of the first sentence, and then SEP token is inserted at the end of each sentence. So as you see here, we have CLS here, SEP here, and SEP here. So it is the beginning of the sentence, but the end of the sentence has two different tokens. We also have segment embedding. A marker indicating sentence A or sentence B is also added to each token. So here basically we have these are all for sentence A and these are all for sentence B. And we also have positional embedding that is added to each token to indicate, and this is like what you're seeing here, from 0 to 10, their position, the position of the tokens in the sentence. Essentially, the transformer stacks a layer that maps sequence to sequence, so the output is also a sequence of vectors with a one-to-one correspondence between input and output tokens at the same index. Training in BERT uses two different strategies. One is masked LM or MLM in short, and the other one is next sentence prediction. So what is masked LM? The idea is basically very simple. What is happening is that we randomly mask, let's say, 15% of the words in the input, and we replace them with a token called mask. Run the entire sequence through the BERT attention-based encoder and then predict only the masked words. based on the context provided by the other non-masked words in the sequence. However, there is a problem with this naive masking approach. The model only tries to predict when the masked token is present in the input, while we want the model to try to predict the correct tokens regardless of what token is present in the input. And to deal with these issues, out of those 15%, for example, that we had, 80% are replaced with a mask token, 10% are replaced with a random token, and 10% of the tokens are left unchanged. And while training, the BERT loss function considers only the prediction of the mask tokens and ignores the prediction of the non-masked one. This still results in a model that converges much more slowly than left to right or right to left models. Another thing is next sentence prediction, or NSP, and this is basically to understand the relationship between two different sentences. A pre-trained model with this kind of understanding is relevant for the tasks like answering the questions. During training, the model gets as input the pair of sentences, and it learns to predict if the second sentence is the next sentence in the text uh, as well or not, like what you're seeing here. The man went to whatever store, he bought a gallon of whatever milk, and then the label is next, but the other one it says it's not. BERT separates sentences with a special SEP token, and during the training, the model is fed with two input sentences at the same time. 50% of the time, the second sentences come after the first one, and 50% it's a random sentence from the full corpus. And then BERT is required to predict whether a sentence is random or not. So this is what we call next sentence prediction. So how does the architecture of BERT look like? There are different types of pre-trained versions of BERT depending on the scale of the model architecture. It could be BERT base with 12 layer, 768 hidden nodes, 12 attention heads, and 110 million parameters, or BERT large, 24 layer, 124 hidden nodes, 16 attention heads, and 340 million parameters. When we can use it and how to fine-tune it is basically the next questions. BERT outperformed the state-of-the-art across a wide variety of tasks under general language understanding, like natural language inference, sentiment analysis, question answering, paraphrase detection, and linguistics. But how we can fine-tune it for a specific hand? BERT, as I said already, could be used for a wide variety of language tasks, and if we want to fine-tune the original model based on our own dataset, we can do it simply just by adding a single layer on top of the core model. For example, say we're creating a question answering application. In essence, the question answering is just a prediction task. On receiving a question as the input, the goal of the application is to identify the right answer from some corpus. So, given a question and a context paragraph, the model predicts the start and end token from the paragraph that most likely answers the question. This means using BERT for our application can be trained by learning two extra vectors that mark the beginning and the end of the answer. For example, the input question could be, where do water droplets collide with ice crystal to form precipitation? And that is the input paragraph, and the answer could be within the cloud. Just like the sentence per task, the question becomes the first sentence and the paragraph the second sentence in the input sequence. However, this time there are two new parameters learned during the fine-tuning, that is a start vector and end vector. And in the fine-tuning training, most hyperparameters stay the same as in BERT training. If you're more interested, you could have a look at the original paper where the BERT is published. That is published by Google AI. Okay, so this is a bit of background of BERT, but what does it look in practice? Installation, basically it's easy. You can clone the BERT GitHub and then download the pre-trained model and start using it. For using BERT, you need to do a bit of preparation of the data. And basically, we want data to be in a TSV format. In column 0, an ID for the row, column 1, the label for the row, column 2, so on and so forth. I mean, if you have a look at their GitHub page, I'm going to put it here, you would see the format of the data. The first step is basically training the model using the pre-trained BERT. And after that, if you want to do the fine-tuning, we can add new layer train to adapt our BERT, as I said before. I'm going to show you the BERT in action soon in another video, so you're going to have a better understanding how the BERT could be used. See you then.